Last time we had talked about the potential in electrostatics part 2. In electrostatics part 3, we are going to see the electrical energy of 2-point charges and of a dipole in an electrostatic field. Electrostatic potential energy of a system of point charges is defined as the work done to bring the system of charges from infinity to their present location. So at first, we are going to see the potential energy of a system of 2-point charges. So let us consider the quadrant, and we have the charge, the x, y and the z axis, the charge q1 at a distance r1. Now let us bring another charge q2 from infinity, which is at a position vector r2 vector, and the distance from q1 to q2 is ab, which is r12. We have the potential at q1. Because it is at a distance r1, V1 is equal to 1 upon 4 pi epsilon naught Q1 upon R1. Similarly, if R12 is the distance from A to B, potential at B due to charge Q1, that is V12, is equal to 1 upon 4 pi epsilon naught Q1 upon R12. So, we can now find the energy stored. W1 is equal to 0 since Q2 is at infinity. If the charge Q2 is brought from infinity to position vector R2, the distance between Q1 and Q2, that is A and B, is R12. Work done W2 is equal to potential at B due to Q1 into Q2. So we have the work done W2 is equal to V12 into Q2. V12 is 1 upon 4 pi epsilon naught Q1 upon R12 multiplied by Q2 gives you W2, the work done. The work done is stored as potential energy. Therefore, U is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R12. Now let us see the potential energy for a system of n-point charges. For 3-point charges, work done W3 is equal to potential at C due to Q1 and Q2 into Q3. W1 is equal to 1 upon 4 pi epsilon naught Q1 upon R13 plus Q2 upon R23 into Q3. Similarly, for 4-point charges, W2 is equal to 1 upon 4 pi epsilon naught Q1 upon R14 plus Q2 upon R24 plus Q3 upon R34 into Q4. Similarly, for n-point charges, Wn is equal to 1 upon 4 pi epsilon naught Q1 upon R14 plus Q2 upon R24 up to Qn minus 1 upon Rn minus 1 into Qn. So, in general, we can write Wn is equal to 1 upon 4 pi epsilon naught summation Qj Qk upon Rjk for all pairs. The charges and location are specific. Now let us see the potential energy of a single charge in an electric field. All this we are seeing in an electric field. So if Q is very small, we assume that the external electric field E is not affected by charge Q. But if Q is considerable, the external electric field and potential vary from point to point. So VR is the external potential at position vector R. Work done in bringing a charge Q from infinity to the given point in the external field is QVR. This is stored as potential energy. So potential energy is charge Q into the potential VR. Now let us see the potential energy of a system of two charges in an external field. So we have the work done to bring the charge Q1 from infinity to R1 as Q1 into VR1. So we have work done to bring the charge Q2. Work is done against external electric field and the work done against the field due to Q1. They get added up. So we get work done on Q2 due to the external field as Q2 VR2 vector, and the work done on Q2 due to Q1 is Q1 Q2 upon 4 pi epsilon naught R12. So by the principle of superimposition, we have work done to bring Q2 to R2 is Q2 VR2 vector plus Q1 Q2 upon 4 pi epsilon naught R12. So from 1 and 2, we get the potential energy of the system, that is the total work in assembling, is equal to Q1 VR1 vector plus Q2 VR2 vector plus Q1 Q2 upon 4 pi epsilon naught R12. Now let us consider the potential energy of a dipole in an external field. So let us have this external field E vector. We have a dipole minus Q plus Q separated by distance 2L. We have the force on this side as plus Q into E vector and minus Q into E vector. So it acts as a torque which gives it a rotational motion at an angle theta. So we have P as the electric dipole moment from negative to the positive charge. Couple acts on a dipole, torque tau is experienced which rotates it. We know that tau is equal to P vector cross E vector. So it is P sine theta. An external torque is necessary to rotate it from theta naught to theta without angular acceleration and at an infinitesimal angular speed. So we have W is equal to integral theta naught to theta tau external theta d theta, that is equal to integral theta naught to theta Pe sine theta d theta. That comes out to be, if you integrate it, Pe minus cos theta theta naught to theta. So we substitute it and we get W is equal to P minus cos theta minus of minus cos theta naught. So we get W is equal to P minus cos theta plus cos theta naught, and W is equal to P cos theta naught minus cos theta. This is stored as a potential energy. U theta minus U theta naught is equal to P cos theta naught minus cos theta, where U theta naught is known as a zero potential. Now let us take the equation again. U theta minus U theta naught is equal to P cos theta naught minus cos theta. Now we substitute theta naught is equal to pi by 2 when the dipole is perpendicular to the field. So we get U theta is equal to P cos 5 pi by 2 minus cos theta. So U theta is equal to minus P cos theta. So U theta is equal to minus P vector dot E vector. Now if the dipole is parallel to the field, theta naught is equal to 0 degrees. So we have U theta is equal to P cos theta 0 minus cos theta. So U theta is equal to P into 1 minus cos theta. So that's about the potential energy of a system of charges. Thank you.